yours. Why is this important? Why these losses? Well, I will just briefly show you. When the signal propagates through the interconnect. So when you have something like this, you have like, let's say PCB, and you have here like some kind of a driver, and then you have your interconnect and your receiver. The amplitude of the pulse here will be exponentially decreased while the signal propagates down the line. What can happen if this attenuation is big enough? Then this digital receiver here will not be able to decode this pulse, and we will have so-called bit error rate bit errors. So that's why we want to have a dielectric below, which has small tangents delta, and this is something which you are going to ask the PCB manufacturer to give you some material, some options, and then you will take that for the simulation to see what's going on there. I will give you one example from practice, what happened in one of the previous companies I worked. There was a very big PCB. I can't remember now, but most probably something like 50 centimeters times 60 maybe. And that PCB had a number of optical transceivers here. These are all high-speed interconnects, and it had some specialized chip for, let's say, mapping and demapping of these signals. Don't bother yourself with that; it doesn't matter. I will just call it ASIC, just that. And they were high-speed connections between all these transceivers. And you know what happened there? This part of the transceivers, they worked normally. And these two, they didn't. So you didn't have any signal here. You could not send, you could not do nothing. And do you know what was the problem there? Well, the problem was the following. The amplitude of the pulses which were sent by this ASIC here, it simply decreased so much that here this receiver could not decode it and convert it to the optical pulse. This also was the case, and these were not. So attenuation here was not enough to decrease this amplitude and to make it useless for these three. And of course, what happens with this redesign of the PCB? That's why you really need to simulate. You really need to simulate and to see what's going on. You will see later on a measurement. I will show you a measurement, how you can even measure that and see so-called eye diagram. Imagine that you have a lot of pulses, like a train of pulses, and imagine that you can store them, first divide them. This is, let's say, a period. You divide this train of pulses in time chunks which are equal to period. And then what you do, you just position them at the same point. So you have something like this. A lot of them. Of course, they will be a bit in this position or this position. They will have some jitter. They will have some lower amplitude. And of course, you will have zeros as well. And you all of them position like this. And you can have literally something like this. This resembles to eye, the human eye. So they call it eye diagram. And I will show you how to measure that and what that eye diagram will tell you. But this is very important for signal integrity. And this could be simulated in this case. And if that was simulated, those engineers would find out that these interfaces would not work. Okay. So now we are proceeding forward. So, okay, you define this stack up, you somehow manage with your PCB manufacturer to get to the right stack up. Then you need to define vias. You need to understand which kind of vias you will need in your design. You see here that we use vias which connect any layer to any layer, basically. This is actually very expensive PCB, and it is called any layer HDI, high density interconnect PCB. That's the most complicated technology and most expensive, and it is used in a very advanced designs. On the right side, you see how this looks like in 3D. I just put that just to give you an impression how it looks like. What you need to remember here is you need to simulate to see if you will have a signal integrity problems. So your amplitude of the signal will be decreased. If you have like a link or interconnect which is like 1 centimeter, or you have like a very big PCB which is like 60 centimeters, it needs to trigger your alarm immediately when you see such big distances and you have high speed signal. You need to simulate and to see what's going on. Otherwise, you will make a mistake. Okay, so we defined the stack up with the manufacturer. We defined vias we need. In some, let's say, non-advanced designs, low-speed designs, you will have only one via. This is through hole via, which connects all the layers. So if you want to connect a top layer, like here with this layer, you will simply use this via here. In the high-speed design, you cannot do that because you will have so-called via stuck. This is the part of the via which is not used. And that can degrade the integrity of your signal. I will not go into details, but just remember, in the high-speed digital design, you should avoid these via stubs. Or if you want to use them, I mean, these two hole vias, you need to perform simulations, 2.5D or 3D simulations. Using someone mentioned yesterday, ANSYS, for example. Okay, so we defined stack up, we defined via types. We proceed something which is called define design rules and control impedance geometries. What is this actually? Well, I will explain you just on a whiteboard. Okay, like this. I will just share it. When you have like a bunch of signals, and you just a second. Okay, here is like here. Stop sharing. Okay. Now, and okay. Yeah. So imagine now you have a bunch of signals in your PCB. It looks like this. So a very, very, very big thing, and you cannot fit all of your signals. And now you are not sure whether you can put, for example, this trace, how close you can put here. Then what you are going to do, you are going to use so-called design constraint manager. remember this constraint manager. It is used in almost all tools. And you are going to define, for example, the minimum clearance between tracks. And when you try to put your track close to the other, you will not be able to do so, or you will get DRC error, design rule check error. So this is very important step. Before you start to do anything on the PC, you need to define these constraints. Why? Because you don't want to finish your design and to find out that your PCB cannot be manufactured. How do you set up these constraints? Well, you will contact or go to website of the PCB manufacturer, and you will find a part which is called capabilities. And there, they will give you a specification, what they can produce. And you will see minimum clearance track to track is, I don't know, like 0.15 millimeters. Then you will see minimum via hole, when we are talking about via. This is the hole, and this is called annular ring. They will say, okay, we can produce minimum of 0.2 millimeter hole. Then you will set up via for your design minimum 0.2, and this should be, for example, 0.5 millimeter minimum. All these things you will find on a website of the PCB manufacturer, and you really need to understand that and to put all that in your rules. Once you finish that, then maybe you will need to do control impedance geometry. We'll come to this later. I will not bother you with this now. And once you do all these things, then you are ready to do your actual layout. Let's just see. So you define the rules and you can start routing. My question to you is, how would you approach the routing? What would be your very first step when you are in the layout design, layout environment, and you need to start routing? What would be your very first thought? What you should do? Think about that. Very, very first step. You have a bunch of components.
I start by um, choosing the position for the component that I cannot change so much.
Yes.
Some constraint because of the form factor of the board or the ports. Where do I want to put the microprocessor or the FPGA? This kind of alignment.
Yeah, exactly. So what will basically happen in industry? You will have some constraints. You will have mechanical first constraints, which says this connector must be here because we have a housing which we are not going to modify, and we need to preserve the same positions. So you need to fix that. When you fix that, then you need to organize your components. You need to partition the design properly. We just tackled that a bit. We saw where the analog front end needs to go, where the, for example, digital part needs to go, and so on. So you need to, in a wise manner, organize that. You need to separate these domains. You need to decouple these domains. That's extremely important. Many engineers, actually, even with a, let's say, long and big experience, sometimes fail to do that properly. So that's extremely important. So the very first step is to properly partition the PCB and place components accordingly. Critical step. Then we do the actual layout, connecting all the corresponding components, create power delivery network, and so on. And what we do at the end, we will run this design rule check to see if we are according to the design rules. for example, you did not check the box that you do online DRC, but you just do at some points because it can be annoying. Okay, so you finish your design. What do you do then? Then you produce some files. Does anyone know what are these files or these images on the right side? Yes, Gerber files. Gerber files. So you produce Gerber files. They look something like this. And you also produce so-called NC drill file. So this is the file which contains where the vias will be actually the holes made in the PCB. When you provide Gerber file, then you provide NC drill file, when you provide your stack up definition, then the supplier should be capable of producing your PCB. That's what you need to provide to them. And then you will get your PCB back. So the PCB manufacturer needs Gerber files plus entry drill files plus stack up information, or so-called ODB++ files. This is some new format. It becomes now standard, but still you can provide Gerber files and entry drill files. In practice, some manufacturers will require Gerber files, other ODB++. You will never make a mistake if you send both. That's, for example, what I do. At the end, you need to assemble your PCB. So to mount your PCB, manufacturer needs so-called assembly data. These assembly data are pick and place file. This is actually comma-separated value file, CSV file, which actually has a component designator and has the coordinate of the component and rotation of the component. And it will just be used to program pick and place machine. Then you need the bill of material because assembly house needs to buy these components, and they will find the part numbers in the bill of material and assembly drawing. And that's all. So this is actually the process we use when we want to actually design and produce the PCB. This is maybe it was a bit overwhelming task to go to this. I selected some things which I thought maybe we should tackle. But trust me, in industry is also overwhelming process when you start. So that's what it is. Do you have any questions? Do you have any comments on this? Yeah. Do you find this difficult, or do you find this it is something straightforward? How do you see this?
I have a question.
Yes.
So you spoke about the approach that you take to the whole design of the project, but then I was wondering if you also have like a review process at some point, like for layout or footprint generation.
Yeah. Very good. Very good question. Very good question. And I will tell you directly my experience, what I faced so far in a different company. So review process is basically mandatory. And how it is properly done, while I was working in Austria, there was one company and they really took very, very seriously the review process. How they took it seriously? Well, the people, for example, engineers who designed the schematic, they would, when they finished, they would give to other colleagues from the same group, which were just doing schematics, and they were not involved in the design. Then these people would take literally like 1 or 2 weeks full time to review the schematic. So they would need to read all the data sheets, to see the reference designs, and to go to the design. This was the very, very best approach I saw in my career. And these PCBs were always first time right. So this other companies, they tackle review processes in different ways. I was in the companies where it was really inefficient way. And of course, if you do like that, you will have several iterations, and that takes time. That also introduces the cost. But very good question. If you want to do a properly review, and what should be mandatory, then you should give it to your colleagues which were not involved in the design. That's how it should be done. But it's not always the case in practice. That's what I would say. Okay, so we finished this part. I would now proceed to this, let's say, real signal integrity and power integrity problems. I will not go into details, don't worry. We will not delve into some big details, but I will tell you something. What you will need to do during your, let's say, professional work when you start working somewhere in industry. This would be my advice. So remember the theoretical concepts you learned at the university, and while you advancing in a technical sense in industry, try to connect the concepts theoretical level to, for example, PCB environment. If you're working as an electronics developer, hardware developer, try to make abstractions of the concept you learned at the university and relay them to the PCB. For example, I will give you some small example. I will just share my screen. I mean whiteboard. Okay. Where this is. Sharing. Okay. And okay. Correct. Okay, we are there. Okay. I will give you an example to better understand what I was talking about. So you can remember that the very basic thing, like from first year of the university, like plain capacitor. Just analyzing that. You would have here connection, here connection. You would have here some dielectric. And as far as I remember, the capacitance was something like area of these electrodes divided by this distance here. There were some abstract things I can imagine on the first year. There were a bunch of some formulas and so on. But when I say to connect that, to understand firstly the basic things and to connect that to PCB, to hardware environment, what you need to do? Well, for example, you have like your top layer on a PCB. You have dielectric below, and you have a ground plane. This is ground. And you have like a traces. Here, trace here, and here. Well, you will have certain capacitance here. You will have certain capacitive coupling. But more importantly, if you have another layer here, and you will make your stack up in that way, that you have a power layer here, you will create PCB capacitor here, which has virtually zero inductance in the lead. You remember what we were talking? We were talking about the inductance of the, let's say, this through-hole resistor and these integrated circuits. And we also that we have some inductance here and here, and that can cause problems. But in this case, virtually we don't have it. Of course, we have it, but virtually we don't have it. And this capacitor you can use to filter very high frequencies. You cannot do that with the components. And what you did, you just applied the very simple thing you used on first year at university. So try to focus on these things when you start working. Try to correlate these things and to translate this what you learned to connect with the PCB environment or hardware environment. That's very important. Okay, so let's just briefly explore this problem with the signal and power integrity. It won't hurt the first presentation. Just a second. Uh-huh. I will switch to another presentation. And after that, we will have demonstration. We will have streaming from the lab. Okay. Let's see where this one is here. Yeah. Workshop. Okay. Managing signal and power integrity challenge. I will just tackle this topic. I just want to make you aware of these things. Just a moment. Let's see like this. And I'll share it. Okay. I think you see this. Okay. So I will not go into some big details here. I just want to make you aware of some problems. So when you design some low speed design, you can do virtually whatever you want. You can do route that in a way that you are just resolving a puzzle. Today I have a colleague, he's a manager, a project manager, and he came to me and asked how much time I will need for some project. And then I told the estimated time, and she said, "Oh, it's too, yeah, very long, you know." And I said, "I will just show you a brief of a part of the design, how it looks like." And he looked at that and said, "Oh, this looks like a puzzle. Yeah, you just need to put the tracks in between, and that's it." That's actually true, but for a very low frequencies, like up to 1 megahertz, maybe even lower. But if you go in some higher frequencies, it's far from reality. So what will happen? I will just share my whiteboard. Okay. So at a very low speed, this impedance here is high. And you basically will just translate the voltage levels in between. But when we increase the frequency, and more importantly, when we decrease the rise time and make pulse something like this, what will happen? We will actually the parasitic component here, and then we will lower this impedance, input impedance, and then we will need to transfer actually the power from this point to this point. And we will need to do impedance matching in order to transmit a maximum power between these 2 points. And we are talking about high-speed digital electronics, but we are approaching actually RF electronics. That's the main problem. Just remember the rise time and the frequency. Big problems. So when these things come into the gate, you cannot do whatever you want. you really need to understand how to transfer power from one pin to another on a PCB, because you have here low impedance. In order to do so, can someone remember that from, I think it was also first year of the university, what is the condition of the maximum power transmission from this point to this point in terms of impedances? I think, sorry?
What is the question? Sorry.
The question is, we want to transmit maximum power from this point here to this point here on a PCB. What should we do with the impedances? At this point, that's actually the main question. Well, in order to transmit maximum power, as far as I remember, we have to have conjugate complex impedance. So we would need to adjust this impedance and to do so-called impedance matching. But we will not go into details. I just want to make you aware of these things. So when you design that, be aware that you can actually create problems with signal integrity. And I will now just briefly mention which one. Just to go on the, yeah, here. Okay. So we mentioned this, ever shortening rise and fall times along with the high frequency signal in machine learning platforms require careful approach to maintain signal integrity. There is another thing, number of CMOS inverters per integrated circuit, digital logic, of course, and high switching frequencies require special design approach to address power integrity. We'll come to that later. Signal integrity problems can arise from various factors that affect the quality and reliability of the electronic signals. That's what we said. And if you do not match the impedances properly, you will cause reflections. What does it mean? So signal will travel along the interconnect, and then it will just bounce back. Part of the signal will bounce back, and part of the signal will continue to travel forward. And you will have some reflections bounce back and forward until you dissipate that energy. And these reflections, they create the problem. Then you can get a crosstalk. So unwanted coupling between adjacent signal lines. So you put them too close. You didn't, for example, simulate that, or you didn't apply some rule of thumb. And you simply have coupling and crosstalk. And then you corrupt the signal. You cannot decode anymore the signal, and you have bit error. About attenuation, we already talked about, and I also give you a practical example what happened in one of the designs. But basically, we have the gradual loss of signal strength as it travels the transmission line. Okay, some additional problems there. You have jitter. Jitter is that your signal, let's say the rising edge does not come always at the same time to the receiver. Sometimes it's faster, sometimes it's slower. And then that's actually the jitter. That's variation in signal timing. And this also can lead to errors because you can sample signal which is not, which didn't come at the right time. And you sample something else and you think it's the right data, but it's not. It's just an error. Signal skew. So imagine that you have a differential pair. Okay, this one is interesting. I will just show you. Okay. Screen. Here. So imagine that you have a differential pair from this to this receiver. and then it goes something like this. And due to any obstacles, this line is longer. Then you will have a skew. You will have actually these signals shifted to each other. And your eye will not be open properly here, and you will not decode properly the signal. So simply speaking, this signal here will have a longer path, and it will arrive here later. This one will come before, and then they will be shifted to each other. So something like this. And you will sample somewhere here. This will be sampled, let's say, properly. This will not be sampled properly. And then you have a B term. So be aware, this is a signal skew. Okay, more or less, these are just listed problems. Now the question is how do we address this mentioned problem? These are very simplified advices. So by controlling the characteristic impedance of the interconnect, it simply means the following. Just imagine like you have one geometry. So this trace is stick here like this, and due to any reason you come to thicker trace. So here you have a different impedance, and you have your signal traveling down. What will happen here? It will just bounce back part of the signal, and part of the signal will go here, because here is transmitter. Sorry. Yeah, I'll then do like this. So what I was showing was the following. You have transmitter, you have your trace. For any reason, trace changes the geometry, actually changes the impedance at this point, and it fetches the receiver. So this is the trace, all this. And the signal needs to go from this point to this point. What will happen? Signal will travel to this here, and then you will have one part of the signal bounce back, and this will continue here. This will be bouncing here in between this continuity until the energy disappears. And also this part here. In time domain, you will see something like this. You have here very short edges. This creates problems, of course, and many other problems. But this is how you cope with this. You will control the impedance, and it means that you will control the geometry of the trace. So you will have a constant width of the trace. But what happens here? You cannot just route straight lines. You need to go here. Then you will have some small discontinuity at this point, but this is inevitable. Okay, so that's one thing. The other is how we control that. To make this one. By selecting adequate dielectrics with low tangent delta and PCB stack up, we already explained that how it influences the signal. It will simply decrease the amplitude of the signal and close this eye diagram. But if you make a proper stack up and you select the proper materials, it will not happen in the extent that you degrade the signal integrity. And of course, you need to do a proper layout. These are just general let's say, recommendations, but the things are much more complicated. Now about the power integrity. Does anyone know what power integrity means and how that influences the design?
You should have a constant power value around all your PCB, taking into account the power drain from different devices, because that could make a slight voltage drop from one point to another of the PCB, and
Mm-hmm.
component is not feeding with the correct voltage.
Mm-hmm. Exactly. So I will just list some things related to power integrity, and then I will give you a simplified version. You will all of you will understand that for sure. So we can have like voltage drop. It's sudden drops in voltage levels due to high current demands, which can cause circuits to malfunction or reset. So you have such a big load that your power supply cannot give that current in that amount of time, and you will inevitably have a drop in the voltage, and you can even reset the device with that. So IR drop. This is voltage drop across the power distribution network due to resistance, leading to insufficient voltage levels at the various points of the circuit. So when you were designing on PCB your power supply rail, that part of the copper, you made it so thin and slim that it has a high resistance. And when you draw a bigger current, then of course you have a big voltage drop, then you can cause malfunctioning. Ground bounce. This is very important. I will just switch quickly to whiteboard. And this is very, very common in all modern circuits, let's say, and designs. So all of you can recognize this stuff. So when you have, this is CMOS inverter, it's used to build any logic in modern CMOS design. So when you go from, I don't know, logic 1 to logic 0 to logic 1, you will have some period where both of these transistors conduct. What practically happens here is that you will connect, like you will almost short circuit the power supply in your PCB with the ground. Now imagine what happens when you have millions of these structures and they start just switching from 0 to 1 at a very high frequency. You can imagine what can happen. It is very hard to provide a power integrity of your systems so that you don't have a malfunction. This is the main problem. But I will explain you how you can tackle that practically. Just a second. Yeah. Just to list all other problems, we have noise coupling. So unwanted coupling of noise from the power supply into the signal lines, leading to signal degradation and errors. I will tell you what we do here with the X-ray detectors. We have a very challenging problem. Why? Because we have a sensor which is very sensitive, and we have a number of rails detector. And what sometimes happens when the design is not really good is that you couple the noise from the power supplies through your power delivery network to the analog front end. And instead of seeing like a proper image, you see some waves on the image, some disturbance somewhere which is not acceptable. This is very big problem in such system. Power supply ripple, everyone is familiar with that. So fluctuation in the power supply voltage typically caused by switching regulators. Yeah, of course, that can introduce noise and affect circuit performance. You need to filter out that. And we talk about decoupling issues. So these are capacitors actually, which should be placed very close to integrated circuit to provide additional energy source, let's say, when you have this switching, so that you do not have, for example, voltage droop. Okay, so how do we address this problem? By proper design and filtering of the power supplies, that's mandatory. That's on the schematic level, basically. By providing low impedance power delivery network and using solid ground and power planes with power delivery network, which are tightly coupled. We talked about that. Okay, so I will stop now here, and this presentation is done. But I will just give you some small tips in the last session, and also after that I will provide you some live presentations, some measurements, how you actually to see on the PCB how it looks like. We can now go to the small break. or yeah, let's start. Um, I will share with you design which we did, and you could just see how we tackled some of these problems I mentioned. Just to turn this off. Yes. Okay. This here. Okay. So just before we start, this part of which we tackled, it actually in industry it is very complex thing, and in general it is complex thing. So there are not too many engineers which can deal with these kind of problems properly. You will need most probably years to understand things and to be able to design boards with such complexity, which have like high-speed digital parts, which have analog parts and so on, and all together mixed in one system. For that, you really need a very big expertise, and you need to be highly skilled for that. I will just give you a tip. You always need to have like a theoretical background on your mind, always. That's on one side. And on the other side, you need to connect that to the practice. You will have some problems in terms of you will design something and it won't work, but it's very important to debug and to understand why it does or doesn't work. Very important. So I will also tell you to avoid common things which many engineers apply in the industry. They just apply trial and error. They are not willing to understand theoretically what's going on, but they're just trying to fix the problem without any kind of understanding. Usually, they succeed after some long time. They succeed usually, but don't do that. So analyze the problem and understand it from theoretical side, and then try to fix it. And that's the only right approach. That's one thing. The other thing, so you will for sure face these kind of problems sooner or later in your professional career. Be prepared. There are some books which can help you to learn the theoretical concepts there. That really helps. Do not use things on the internet you find, some rule of thumb, some tips, tricks, whatever, on some forums. And I read a lot of these things, and I can tell you most of them are crap, complete crap. So don't learn from that. Learn from the books. That's another thing. Um, Now I will just show you this design, which we were talking about, which we were used as a test vehicle or learning vehicle, how things should be done and so on. Of course, for this, let's say, short time, we cannot cover these topics. This is just to give you an impression what's going on, and to see the level of complexity and what is waiting for you when you start to work in industry. But don't panic. You will, of course, adopt these things. You will learn them. You will have older colleagues who will help you, and that's all. Now I'm going to share my screen just to show you this design in Altium, how it looks like. Okay, you see nothing, I can imagine. There is no design. I'm joking. So this is a project panel, and this is the name of the project. Now I will expand this. I will briefly just walk you through that. You will see the schematic part and the PCB part, but I will not go into the details of schematic, not at all. I will just show you how this looks like. There is one sheet which I strongly advise you to make when you do designs. It is called, I call it top design. And this is just top level of the design. So you see here major blocks. You see power supply, eMMC, microcontroller IOs, FPGA IOs, analog front end. And these are just the coupling caps for microcontroller and for FPGA. So these are interconnects. These are the name of the signals. This will help you. So this is a top level diagram. It will help you to structure your design and to be able to draw that and design that efficient. Do that. Whatever tool you use, you have this capability in that tool. Power supply. It looks like this. We are not going to go into details, just to give you a rough feeling how it looks like. So this is a power tree which is implemented, and this looks like this. I call this a microcontroller power supply. These are just the coupling caps and some filtering, very hidden. And I also put here the crystal, which is used to clock the microcontroller. For the FPGA, it looks like this. A lot of decoupling caps, they need to be placed very close, of course, to the chip, because this is BGA. It's on top layer. You place decoupling caps on bottom layer. That's very good in terms of low inductance. These are just the IOs of the microcontroller. You can see here that we have these connectors for altimeter. This is serial wire debugger connector. This is for GPS. For GPS, we have a load switch here. For short range radio, we have also a switch here. We can turn it off and on using microcontroller and so on. But we are not going to go into details. Then we have IOs of the ARTIC, of the FPGA. This looks like this. Then we have UNMdP. This looks like this. And we have analog front end. It looks like this. No details, just a top overview, just to give you a rough feeling how this schematic looks like. This is not a big schematic. These are just like 6-7 pages. Schematics are for bigger systems significantly bigger, and you really need time to do that properly. And sometimes few of them are going to work on the same schematic. Now I showed you the photo of the rat nest. There was a reason for that. That it was a photo. You can remember. Why I show you that? We are now in schematic, and now we want to transfer this design to the layout environment. Okay, we will firstly compile this design, validate, and we will see here messages. Okay, successful, no errors found, no problem. Then we want to update our PCB. This is the PCB we already did, and this is the empty. This is just for workshop test. I will update this because there are no components. If we open that environment, I will open it. You will see how it looks like. Nothing. There are no components. So our CAD tool will now work for us. We will tell the CAD tool to move all these components into layout environment. From the symbol to the footprints. Let's do that. Import changes. Let's import. Okay, we have a pop-up window. It asks us add components. 352 components. Add. Okay, we say yes. Add these components. Let's see what else this asks us. Add pins to the nets. Yes, add pin. And if we'll add these pins, so on and so on and so on. Let's see if there is something else there, which this tool wants to ask us. Oh yes, add component class members. Okay, yes, each component is class member here. Doesn't matter. There are rooms. We don't want. Okay, let's put rooms. No problem. We now say execute changes, and now the software works for us. It now translates these symbols into footprints, and it will put now that into the environment. How does it look like? It looks like this. So all these lines here, what are connecting these components? They are here. They help us when we root. Why I showed you rat nest? Because this resembles to rat nest. If we now compress these components here on the PCB, you will see on a very small, let's say, area, a lot of these rat's nests. And that's how it looks like. You need to resolve somehow all this. So this is not a simple task. If you plan to use auto root, don't do that in designs like this, because you will completely screw up the design. It will not, most probably it will not work. You will connect everything and you will have all nets rooted, but design most probably will not work. So you really need to understand what you are doing there. And there is no shortcut. Still, there is no AI tool for this, to do this effectively. So there is no shortcut. You need to understand that theoretically properly, and you need to put your theory in the practice, and you need to do designs, and you need to make mistakes, and you need to debug mistakes, and you need to understand what mistakes were. If you don't do like that, you will be like the majority of the engineers in the industry. Trial and error, trial and error. Don't do that. Okay, let's see how this design actually looks like. I will close this, don't save. Let's go here. This is a 3D model. I will switch to 2D. I will turn on all the layers. So I will show you on the left side, you see all the layers. We have here 8 layers. So this PCB has 8 layers. These are some, let's say, layers which are not connected to the PCB manufacturing, except this overlay. Overlays are just writings on a PCB. You see, for example, if you want to designate your PCB, you can write something. This is that layer is used for that. But we are just now interested in these signal and plane layers. Signal and plane layers. I will now identify the major component. I will do that in 3D because it's easier to spot the component. Okay. So you will see how I did partitioning of this design. Here you can notice, first of all, the USB connector, and this is a PMIC which arbitrates between this connector. This connector is used for the battery. This is for USB. So this arbitrates and it pushes forward the voltage. This is PMIC for FPGA, which is here. And this is for the microcontroller, which is here. So we have power supply in this region. We have a digital part in this region. And we have analog part in this region here. So what you see, what you observe here is the following. Power supply section, which has a lot of noise, is really apart from the analog part of the design. So they are really decoupled, spatially decoupled. But that's not enough. But we will not go into details. And in between, we have this digital part. Yes, it needs to be here because you need to connect your ADC to your FPGA. You need it. So they need to be next to each other. You see some molding here, some cuts. I will not go into details. You will face this in the practice. Just remember this as it looks like. We have some components on the bottom. Here is the part where FPGA is. And here is the part where the microcontroller is. You can see the caps here, the coupling caps. They are very close, basically. You see some other caps here. This is some, I think, level translator. I can't remember. Doesn't matter. And this is also the part of the very, very imp of the analog front end. You can notice that I put this in the bottom layer. And you can notice that power supply and these components are on the top layer. I did that on purpose because there is a ground plane which acts as a kind of a shield. So I want just to decouple this even further, putting this on the bottom side. So this is actually how the PCB looks like. Do you have any questions so far? Do you have some observations, some comments? Do you follow the presentation? More or less. More. Okay. So I would not bother you anymore with this. This I just wanted to show you the end result of the design, how it looks like. So with this, we wrapped up design. We wrapped up these problems about, let's say, signal integrity, power integrity. I can just briefly show you, for example, how differential pairs are done from the ADC towards FPGA. It's very short thing. This is where the clock generator is positioned. I will just turn on some other layer. So the second layer is the ground layer. There is no track. It uses the return path layer for the top layer. Then we have a power layer number 3. This is, for example, one power delivery network. This is, for example, another. Then we have another layer of power. It looks like this. Here we have different delivery networks with different voltage rails. This looks like this. Then again, ground layer. This looks like this, ground layer. Then we have another signal layer. Someone commented that we should maybe have clock lines, differential clock lines in as a strip lines. Yes, they are done here like that. Again, ground layer. So you see the signal layer is sandwiched between two grounds. And these clock lines, they are sandwiched here in between these two grounds. And then we have a bottom. Yeah, some small signal. But what I want to say is, you see that in the bottom layer, if we click here, this is a very big polygon, which actually it is ground. And where you have here the traces, this is just opening for this trace not to be short-circuited. All this big blue area, which is actually copper, and it is connected to the ground. This is how it looks like. So where you see this black thing, there is nothing there. Not any copper. And you see this blue, there is a copper, of course. Yeah. So I would not go into more details. I think it's enough. And now I will just show you some live measurements. Two types of them. I will stop sharing this. Okay. So I will give you just a hint what we are going to measure. I have here with me one USB cable. This USB cable is, of course, consists of like 4 lines, USB 2.0. It has power, ground, and it has one differential pair. We want to see the impedance discontinuities on this cable. We want to see that. And on the other side, it is connected to this small development PCB. This small development PCB connects this part of the cable here. So this whole system can be connected to some host system, which is a desktop or notebook. But it is very important that we preserve conductivity of this interconnect goes from this connector to the cable, to the PCB, and to this system on chip here. Actually, this is a microcontroller, but they name it as on chip. It has different peripherals there. So we want to see what will happen when we want communication between notebook and between this embedded system. What will happen with our signal if we can have a communication, because maybe the eye diagram is close, too close. Actually, the amplitude of the signal is too small, and we cannot decode the signal. We don't know that. So we just got this PCB today, for example, and we want to test it, Don't know anything. According, for example, to simulations, it should work. How do we do that? Well, we need a device, a measurement device for that, which is called the TDR, time domain reflectometer. So to see the impedance profile. Do you know what is the differential impedance for USB 2.0 by the standard? It is 90 ohms. We should measure 90 ohms. We have some discontinuities here at the connector and on this side where the connector is. But the cable should be 90 ohms. The differential pair on the PCB should be 90 ohms. And we should see some discontinuities on the line. That's what we expect in our measurement. So we will see that, yeah, 90 ohms, we expect some discontinuities. That's one thing. And we will use scope and some software on PC to see the eye diagram of this interconnect. Interconnect, I'm repeating, consists of cable and the space on the PCB. Okay, is this clear? Or do you have questions with this? No? Okay. What I'm now going to do, I'm going to share screen from this setup I have here, and I will turn on the camera so that you can see what I'm doing. Okay. Do you see my screen?
Yes.
Okay, I will just use this camera to show you briefly what I have here. I have here a scope. I have here PDR. And I have here this special fixture, which will help me during the test. It will also provide, yeah, let's say a proper test setup and eliminate some errors in measurement. Okay, so what I'm going to do now, you see here many ports, so we can really test the different aspects of USB interconnect, but we will now focus firstly on the impedance profile. What I'm going to do is I'm going to connect the this cable of the TDR. I'm going to connect it to this fixture here. Okay, I use this tool because it provides a constant moment. So you always screw this to the. You hear the click. One click. It clicks when it achieves the moment. So it's always screwed in the same way. Okay. What we need more? Most probably we will need this. This is connection to the computer. And we need to power supply this fixture. And what we are now going to do, we are taking our device under test. Device under test. And we are going to connect this cable, this test port. What will happen in this setup? Just simplified. I will not bother you with the details. So signal is coming outside the PDR to these cables. It will encounter here on these connectors some reflections, of course, because we changed the geometry and we changed the impedance. It goes here on the traces on the PCB, and then it comes to our cable. I will not bother you with the calibration and these things. Just forget that. But we can calibrate and we can make calibration plane actually here. Maybe also here, but doesn't matter. Forget about that now. So the signal propagates and comes here. Here again, it experiences some reflections because we changed the geometry of the interconnect, so we changed the impedance. Then signal propagates to this cable, and finally it comes here to this cable, to the tracks on the PCB, and goes to this SoC here. So with this, we will see the profile of the impedance which signals encounter while it travels down the interconnect. Is this clear? Yes. Okay. Now I'm going to switch to some application we are going to use. This is application which controls the TDR. Okay, now we are connected there. You see my screen? Yes? Okay. We just need to give the name of the measurement. That's what application requires. I'll just call it test. We have differential pair, so select measurement mode. Okay, we are already in differential, no problem. I will not bother you with some calibrations and stuff. Just forget that. I actually already did it, but okay. So we just start acquisition. We're just now start setting the boxes. And we are measuring the reflections. And it's done. So there was a train of the pulses. We measure the reflections, and based on reflections, we can calculate the impedance mismatches. And not only impedance mismatches, we can see the impedance profile. What I'm talking about, you will see in a second. Results, no results, but we can go here. And we see something like this. This is a problem. This I will just redo this. And okay, we repeat the procedure. Okay. German. This is the usual stuff when there is some strange. Turn on and on this. This is turn. Yes, now I will turn on again. Okay. Okay. Second. Okay, I really fixed it. Just a moment, I will need to restart this. I'll stop. No. Moment. Yeah. Okay. I will just need like 1 minute. Basically, what you are going to see is just the impedance profile. So when the signal hits the discontinuity, it will reflect back, and this will all be recorded, measured, and then the device is capable of visualizing literally the impedance profile, and we will exactly see what's going on in the interconnect. Okay, I will just need this part. This, That will take, I think, a bit more, but just to set up again. Okay. Yes. Okay. Oh, this really crashed actually. I don't know what's going on. Yeah, let's do like this. We'll just share one of the previous tests I have with you. Just a second. Okay. Okay. It's here. Okay, I'm just sharing my screen now, and you will have a look on the. Can you see my screen? Okay, so what we can see here, actually, I don't know what happened with the application, but it crashed. And yeah, we see that when we launch the signal, test signal, we encounter 100 ohms. And these 100 ohms are actually from the cables. You saw these coaxial cables. They go differentially in 100 ohms. Then we encounter discontinuity. We see that this discontinuity introduces this profile of the impedance. This is 100 ohms. And then you see that we are entering the cable here. I'm here representing two overlap diagrams from two different devices here. I did some measurements in the past. So this is green is one device, one measurement, and the red is another device. So you are just looking at two devices overlapped each other. So you see the red one, it's almost 90 ohm. And signal propagates and it encounters basically 90 ohms and it goes almost to 100 ohms. This continuity here is when the cable connects to the PCB. And we come here to this point. You see a drop in the impedance, but this is very short track, and then it goes very high. It means that actually the signal encounters the open side, which is to be expected. So this is how the impedance profile looks like. And we can say that this one is okay. Why? Because you have 90 ohms differentially, but you have a tolerance of plus minus 10%. But the green one, it clearly violates the impedance profile required. So this is more than 99 ohms here, clearly. So with another device, we have a problem. So this is how you perform measurements to check how the impedance profile looks. And this is very handy tool in practice because you can really measure what you design. But you need to be aware of the, let's say, inaccuracies of your measurement. And you also need to be aware of the problems which are introduced not by your design, but by something else. So in this case, we see this part. This part is clearly not a part of the design. But you know, you need to know what you are measuring. And before each measurement, you need to visualize basically in your head what what you need to expect if the device and the performance be okay. Okay, so I will now show you another measurement. The measurement is used to measure the eye diagram. I will just turn on the camera here. Just a second. Okay, so that you can see what we're measuring. Okay, we'll now go here. Just to turn on the camera again. Okay. These lights. So, okay. Can you see my screen now? No? Okay. Let's try this again. Can you see it now? Okay, we are again there, and we are again with our fixture. So this part was used for TDR measurements. Now what we would like to do, we would like to measure the eye diagram. There is another connection here, which is used for that. But in order to do so, we need to connect the scope to the our fixture. So how do we do that? There are another cables. I'll go here. On the PCB, these cables and these connectors are connected to the traces so that we can record the signal. We can measure the signal. And I will briefly explain how this measurement setup works, because we also need some software here to configure our end device. Okay, this guy here. So just briefly, when we connect this device here, what we actually did. This goes there to the station, to the desktop, and this connection goes directly here to this device. So this device is basically now connected to the desktop normally, like any other USB device. But this fixture here helps us to actually access the data lines in some convenient way with these just SMA connectors. So no big discontinuities, just connector. We are not using like a probe, ground lead, and so on. So no, this is very, very convenient. What will happen now? We will start the application on the PC. The application will communicate with this USB device and put the device in the test mode. So the device will start to send test packets on the line. Just send through this cable to the test station. But we are connected to the data lines with this, and we are going to measure the signals with the scope. Scope is capable of storing these signals and to align them so that we can make an eye diagram. And you will see how it works. Hopefully it will work. Okay, I'm going now to switch to the application. The application is called, yeah. So let's see if we can connect scope. Oh yeah, it's 5, that's good. Let's start the test. It's already set up for USB 2.0 and so on. We are now connecting to the scope. Okay, we will say, I don't know, device and a test device. We say yes. And now what's going on? The scope is connected also to the this test station, and test station is now configuring the scope to the right measurement setup. It will finish soon. Okay, so now the application tells us that we connect a number 2 port of scope to D+. I think I did so. Number 2, yes. Plus. Okay. Then there are some further configuration. And then we get a message from the software what we need to do. Make sure the test in its on the fixture in its position. Okay, I already did that. Start HS electrical test tool. That's the tool. So we started. It just says select host controller to load into test second. That host controller is on this station. We say continue. Now it says start, select device and click test. Okay, this is device test. Yes. And then it says enumerate bus and verify the device appears in the selected window. Let's try. Now I will just disconnect this and connect it again. No, I don't know. Today simply I don't know what this was tested already. Okay, never mind. Obviously something really badly broke. But doesn't matter. I'll show you some tests which were done before. How it looks like actually. Okay, there is a report. This is what I'm talking about. So here, when you finish this measurement, obviously, I don't know, this computer crashed badly. I don't know what's happening here. But this is actually the diagram, which you get in the report. And how you actually interpret this. This is called the mask here. And this mask defines a minimum opening of this eye diagram. If your signal collides with the mask, for example, this is very close, but if this collides with this part here, then we would say that our link interconnect does not provide a first integrity. And we then need to design something. So this is how you actually do this in practice. Do you have any questions about it? Okay. So I will just stop sharing. I really don't know what happened with the with the whole computer, why it doesn't work. But basically, you understood the point. You have two kinds of measurements. One is to see impedance profile, and the other is to see the eye diagram, how it looks like. Both of them need to pass that you can say that your interconnect provides a proper signal integrity. Okay, so if there are no more questions, I would conclude this presentation for today. And what are we going to do tomorrow is I will just briefly mention design for EMC, but don't worry, I will not go into details. I will just for, let's say, some kind of a top level, so to provide you some more or less general information and maybe some small details, but not too much, so don't worry. And when we finish the C part, then we will proceed to the exercise, the task. So I will give you some requirements for some system. It is also a system which is already implemented, and let's see your proposals. The system which will be implemented in the greatest details, I would say, that system will be yeah, the best, and the author will get the prize. Okay, so if there are no questions anymore, I wish you a nice evening and see you tomorrow.
Thank you. Bye.